Okay, we have a special treat this week, the 5th annual Thomas and Yvonne Williams Lecture for Advancement of Logic and Philosophy. And here to introduce our distinguished speaker is Scott Weinstein in the Philosophy Department.
Thanks very much, Jim, and thanks also to our colleagues in mathematics for including this lecture in your colloquium series. On behalf of the School of Arts and Sciences and Penn Engineering, I am very pleased to welcome you to the 5th Thomas and Yvonne Williams Lecture for the Advancement of Logic and Philosophy. We are most grateful for the generosity and vision that Tom and Yvonne have shown in establishing the fund that supports this series of lectures and that makes possible other educational activities at the university and at upper schools in our region. It was a great pleasure to work with Tom when I first arrived at Penn and to watch him develop through the study of logic and philosophy that clarity of mind which he has so successfully brought to bear in the sphere of practical affairs, and that sustains his ongoing passion for the life of the mind. And it remains a great pleasure to work with him now on a range of activities that will advance a general appreciation of the power of reason to clarify problems, both practical and theoretical. I am delighted to introduce this year's Williams lecturer, Hugh Woodin. Dr. Woodin is a professor of mathematics at the University of California, Berkeley, and is one of the leading set theorists in the world. In 1988, he shared the Carroll Karp Prize, which is awarded every 5 years by the Association for Symbolic Logic, for his contribution to establishing from the existence of a supercompact cardinal that the axiom of determinacy holds in the smallest transitive model of ZF containing all reals and all ordinals. Dr. Woodin's point of view, his deep results, and his bold conjectures have elucidated fundamental questions of set theory, among them Cantor's continuum hypothesis, the first of Hilbert's celebrated problems. Please join me in welcoming Hugh Woodin, who will speak to us about the continuum hypothesis and the search for ultimate mathematical truth. Thank you.
Well, I'd like to thank the philosophy department and the mathematics department for hosting me, and you're very lucky to have someone like Tom to encourage and make these lectures possible. So thank you. And I should point out, we do have a logic program at Berkeley, and we would love to have similar sponsorship of okay, so I probably have too much to do. I believe I have an hour, right? Okay, so and it ends at 5, correct? And that clock says 3:05, so that means I have a little bit longer. Anyway, so I want to talk about the continuum hypothesis, but more I want to talk about trying to come to an understanding of the universe of sets, or at least what the nature of truth should be. So let's see if this works. Good. Okay, there it is, the universe of sets. This is a cumulative hierarchy. You start with nothing, and at a successor step, you collect all subsets of what you already have. That's the power set. And at limit stages, you take the union. So that's our object. That's the universe. And unfortunately, we have axioms for it. The ZFC axioms are the formal theory. And unfortunately, that theory leaves basic questions such as that of the continuum hypothesis unanswered. So let's recall what the continuum hypothesis is. That was the founding question for the study of set theory. And this is due to Cantor. Suppose you have an infinite set of real numbers, and the continuum hypothesis asserts that that set is either equinumerous with a set of integers or equinumerous with a set of all real numbers. In other words, it has either countable cardinality or cardinality of all the real numbers. And by the results of Gödel and Cohen, this problem is formally unsolvable from the axioms. But this doesn't mean it doesn't have an answer. So most of this talk is devoted to trying to justify that claim, but before I talk about the continuum hypothesis, I want to look at some other unsolvable problems. All right, so I'm going to just define, I have to set up the problem. So let's look at two very simple operations that you might undertake on subsets of Euclidean space. The first is just complementation. If you have an input set, the output's the complement. The other is projection. Now here, so maybe a geometrical operation, you have a subset of Rn plus 1 and you project it out onto Rn. So if it was a subset of the plane, you'd be taking its projection onto the x-axis. So we'll define a set to be projective if you can generate it in finitely many steps from a closed set in some higher dimensional space. So the projection is a dimension lowering operation. Okay. The general measure problem is every projective set Lebesgue measurable, and does every projective set have the property of Baire? And recall that you have the property of Baire if you differ from an open set by a meager set. There's a more technical problem, the uniformization problem. There's a formal definition, but it's a little easier to draw the picture. So here's the projective subset of the plane. Here's the coordinate axes for reference. And you'd like a function that in each section, if the section is non-empty, picks a point. And you would like the graph of that function to also be projective. Now, if you relax that and you don't require this, well, of course the function exists as a consequence of the axiom of choice. But the axiom of choice doesn't guarantee you that the function that's produced is projective. So you might call this as some kind of effective version of the axiom of choice. So these are two classical questions. They arose in the early 1900s. And Luzin predicted in 1925 that we will never know the answer to the measure problem. And I might draw an analogy to the predictions you might hear now. We'll never know the answer to the continuum problem. I'll get the hang of this in a moment. So now I'm going to talk about infinite games. If you have a projective set or any set of real numbers, there's an infinite game you can associate to that set. It has two players. We think of the players as constructing an infinite binary sequence, or more formally a function from n into 0, 1. Player 1 gets to go first and specify the first value. Then player 2 specifies the second value. Then player 1 gets the turn and so forth. After infinitely many stages, they've specified the function. And then the winning condition, the winning condition, player 1 wins if you take that sum. If that real number is in A, player 1 wins, otherwise player 2 wins. So look, if A is empty, 1 can't win. If A is everything, 1 always wins. Okay, so we say that a projective set is determined if there's a winning strategy for either player in this game. A winning strategy is just a function. It associates to the current state of the play, of the game, the next move. So formally, a strategy would be a function from finite binary sequences, that's the state of the game, giving values 0 or 1. Either player can elect to follow that strategy. It's, say, a winning strategy for player 1, if no matter how player 2 plays against that strategy, if 1 follows it, 1 always wins. So a winning strategy, you can't have winning strategies for both players, you just play them against each other. So this is an infinite game. If it were a finite game, then by von Neumann's theorem, there would be a winning strategy or drawing. But for infinite games, that's not the case. So the axiom we want to look at is projective determinacy. It simply asserts that for every projective set, there is a winning strategy in the game given by that set. Now, I'm not doing history justice here. The projective determinacy was implicitly introduced in the early 60s. It was realized within 15 years that it was an incredibly fruitful axiom. And it was shown in a beautiful piece of mathematics to solve both the general measure problem and the uniformization problem. And I should say, those problems were unsolvable otherwise. So superficially, take the uniformization problem. That's unsolvable exactly like the continuum hypothesis is unsolvable. In fact, if you take the two universes that canonically are cited to indicate that the continuum hypothesis is unsolvable, Gödel's constructible universe and the extension of that produced by Cohen, that same pair of universes shows that the uniformization problem is unsolvable. Okay, but projective determinacy solves it. It gives a positive answer to the general measure problem and a positive answer to the uniformization problem. But is the axiom even consistent? Well, we're going to attack this problem in two steps. So the axiom was introduced in the early 60s. By the early 70s, it was known to solve the classical questions about the projective sets, but then the consistency became an issue. Again, I'm not saying everything that happened, but certainly a seminal theorem in the subject was the Martin-Steele theorem of 85, so almost 25 years ago. Suppose there are infinitely many Woodin cardinals, and I'm not going to define Woodin cardinals, then projective determinacy holds. So the short version of this is that large cardinal axioms, or axioms of strong infinity, outright imply projective determinacy. Whoops. Whoops. And then there was about 2 years later, I proved the theorem that it gave an exact match. In fact, gave an equivalence to projective determinacy in terms of the large cardinals. So the formal and technical theorem is projective determinacy is equivalent to, for every finite n, there's a countable transitive set or a model. M is iterable, and M is a model of the axiom ZFC, plus there exists at least n many Woodin cardinals. What this theorem shows is that you can't really improve this theorem. You can't prove projective determinacy from finitely many Woodin cardinals. And so that was considered the ultimate validation of both the consistency and the truth of projective determinacy. So I'll make the claim projective determinacy is true. Now, obviously, I have I'm biased on that because I'm going to say Woodin cardinals exist and Woodin cardinals imply projective determinacy. Anyway, it's, I think, clear given the analysis that's been done, is projective determinacy is the correct axiom for second-order number theory, just as the classical piano axioms are the correct axioms for number theory. So second-order number theory is concerned with this structure. Second-order number theory is concerned with this structure. You add all sets of integers. Now, if you're going to have all sets of integers, you better know which integers are in which sets. So this is the structure for second-order number theory. This is the structure for number theory. We've had the axioms here for quite a while, the piano axioms. It took a long time to unravel the story there. So there it is. We have the axioms for second-order number theory. It just took a while to find and validate the axioms. But if we go back to the rank hierarchy, this all concerns V omega plus 1, which is just an infinitesimal fragment of V. So now we want to move beyond this fragment and try to understand the universe of sets itself. Remember, we very least would like to understand the continuum hypothesis. So to do this, one should try to understand why people are claiming that the continuum hypothesis has no answer. The reason they're claiming it is Cohen introduced a very powerful method for taking, if you're in a universe of sets, of constructing an extension of it. And in that extension, you can make the continuum hypothesis either true or false. Think of an analogy with fields. Cohen really discovered the analog of an algebraic or transcendental extension of a field. Structures or models of set theory are vastly more complicated objects, so the extension problem is much, much more difficult. Okay, so if that's the ambiguity, then maybe we should say, well, maybe the correct picture is here's in a seed universe, and we apply Cohen's method to get to this universe, and maybe it could also come from this universe, and then we move out to this universe and so forth. So we imagine that we start at V, and we see what universes we can visit by Cohen's method. That's some kind of multiverse. And maybe that's the correct conception of truth. The trouble with such a thing is the philosopher will instantly and correctly say, where is that happening? V is the universe. What are you talking about? There's a larger universe? And if so, isn't that really V? So if you're going to have truth based on a multiverse, and that's what this is suggesting, a sentence is really true if it's true in each universe of this generic multiverse, you better be able to formalize it within V. Otherwise, you really need that meta-universe in which the multiverse is being constructed. So this was realized about 2 years ago that you could formalize this. But this is a theorem that could have been proved by Cohen right after the development of forcing. It's just people weren't thinking that way. So there's a transformation, an explicit transformation. You have an input sentence phi and an output sentence phi star. And the following are equivalent. Phi star holds in V if and only if phi holds in each universe of the generic multiverse generated by V. Now, as stated, this is a triviality because phi either does or does not hold, and if phi does, I could take phi star to be 1 equals 1, and if phi doesn't, I could take 0 equals 1. The point is that this transformation is independent of V. It's an explicit transformation. It doesn't matter what V is, it's just an explicit transformation. So the good news is that this suggests a conception of truth, namely this multiverse conception of truth. It can be reduced to any constituent universe, and you don't really need the meta-universe. So maybe this is it. So we can explore this. Maybe we can explore this. Maybe not. Nope. Okay. But there's a serious issue. Now, this is a subtle point which I'll come back to later. If one's going to adopt the multiverse conception of truth for arbitrary sentences, no matter how complicated, then how does one justify the restriction to set forcing extensions as opposed to class forcing extension? Cohen introduced what might be called set forcing. Those are extensions whose blueprints are partial orders. But there's a class version of it that can, if you'd use that extension, it perturbs the universe throughout the height of the universe. Okay, so let's restrict. So I'm going to be making some definitions, and I'll try not to do more than 4. A sentence is rank universal if it's merely saying some other sentence holds in V alpha for all alpha. So V alpha is a rank. Rank universal means this sentence is asserting something happens in every V alpha. If you negate that, you have a rank existential sentence. It says there is a rank in which something happens. So the continuum hypothesis is expressible both as a rank universal sentence and as a rank existential sentence. That's an elementary set theoretic fact. So let's restrict consideration to rank universal sentences. The idea is this objection to the generic multiverse given by set forcing. It seems reasonable that if we restrict to rank universal sentences, that's okay. So we're just going to narrow down to the rank universal sentences. So the claim is that the generic multiverse conception of truth for this restricted class of sentences, rank universal sentences, is implicit in the argument that the formal independence of the continuum hypothesis, as demonstrated by Cohen's method, shows that the continuum hypothesis has no answer. It doesn't distinguish the continuum hypothesis from any other rank universal sentence. So now this is something we can analyze, or try to analyze. So for this analysis, one introduces a new logic. This is called omega logic. This was introduced about 10 years ago. So here's a formal definition. It doesn't seem to have anything to do with the generic multiverse. Again, we have a rank universal sentence. We'll say it's valid or logically true in this logic if it holds just in all generic extensions of V. That's not the generic multiverse generated by V. You're only allowed to go out. So the difference is V, you can go straight out those are the generic extensions. You're not allowed to back up and go out again. You're not allowing that. It's just outward. But there's a remarkable consequence of large cardinal axioms. If you have a proper class of Woodin cardinals and phi is a rank universal sentence, then phi is a generic multiverse truth if and only if it's omega valid. So what that is saying is that if you have a rank universal sentence and you want to tell whether it's true in the generic multiverse, you only have to look at the extensions outward from you. You don't have to worry about backing up and going out and backing up and going out. So that shows, for example, that for a rank universal sentence, whether to assert that it's a generic multiverse truth is itself a rank universal sentence. Okay. So now I want to introduce the proof relation. It's a little technical. So if you have a set of reals, we'll say that it's universally Baire. If its continuous pre-image in any topological space has the property of Baire in that space, that means differ from an open set by a meager set. Generally, you're only going to consider those topological spaces S, which are Baire spaces. If the space itself is meager in itself, then it's a trivial notion. Example, Borel sets are universally Baire. So it's some kind of generalization of the Borel sets. In fact, if you have a proper class of Woodin cardinals, the universally Baire sets define a transfinite extension of the hierarchy of the projective sets. Every projective set's universally Baire, but the universally Baire sets go well beyond. They're all determined if you have the large cardinals. Okay, so the universally Baire sets really trace back to determinacy. They're a special collection of sets of reals. Okay, so we're headed toward the proof relation. It's the universally Baire sets that are the proofs. So the proofs are not finitistic objects. So to make sense of that, I have to introduce another notion. If you have a universally Baire set and you have a countable model of ZFC, a transitive model is just a transitive set. That's a set that's downward closed. If A is an element of M and B is an element of A, then B is an element of M. We say that the model is strongly A-closed if we look at all the models we can reach from the initial model by Cohen's method. We're only going out. Then A intersect N is in N. Sorry. There. Oops. So if M is strongly A-closed, A intersect M is in M because M is a Cohen extension of itself, but this alone does not suffice. It's a stronger notion. Okay, so now I can make I think I may switch to the arrow keys. And now I can define the proof relation. You have a proper class of Woodin cardinals, a rank universal sentence. Remember, those are the sentences we're interested in for now. We'll say it's provable in omega logic. If there's a set of reals, it's got to be universally Baire. And here's the notion. If you take any countable transitive model, if M is strongly A-closed, then M thinks the logical relation is true. So what's the analogy? If you have a universe which sees the proof, then what's purported to be true, proved, is true. See the proof, in this case, is strongly A-closed. Think that it's true means just valid. So the proof, in this case the universally Baire set, is enforcing the logical relation. Okay? So whenever you have a proof relation and a logical relation, the first question is soundness. Okay, so we have our two notions. We have the proof relation and the logical relation. First issue is soundness. If you're omega provable, this is again for rank universal sentences, then you're omega valid. Remember, omega valid means not only are you true in V, you're true in all generic extensions of V, or you're true throughout the multiverse. So now one wants to know whether the converse is also true. That would be the completeness theorem for omega logic, and that's the omega conjecture. Suppose you have a proper class of Woodin cardinals, and phi is a rank universal sentence, then it's omega valid if and only if it's omega provable. Okay, that's open. Okay, so I'll state the theorem, which one might call the fundamental theorem of omega logic, because we can't prove the completeness theorem. Suppose you have a proper class of Woodin cardinals and the omega conjecture holds. Look at the set of all rank universal sentences which are omega valid. That set is actually definable in V omega plus 2. Okay, remember, omega validity referred to the whole universe of sets. And yet, something miraculous happens. The set of validities becomes provable, definable in V omega plus 2. Think of the analogy with first-order logic. There, the validities would be the provable sentences, and the provable sentences are certainly true in arithmetic, definable in arithmetic. Okay, now there is so therefore, if you're going to take the generic multiverse view of truth for rank universal sentences, it's just a version of formalism. You're saying that the rank universal sentences that are true are those that are provable in omega logic, but that set of sentences is itself definable in V omega plus 2. So, the summary is that if the omega conjecture holds and you have a proper class of Woodin cardinals, then the independence of the continuum hypothesis as demonstrated by Cohen's method certainly does not establish that the continuum hypothesis has no answer. You can't distinguish the continuum hypothesis by virtue of that argument from any other rank universal sentence. All you're doing is saying to be true or to have an answer, you must be a generic multiverse truth. But the set of generic multiverse truths is itself definable in V omega plus 2, so you're in the uncomfortable situation of saying truth in V is reducible to truth in V omega plus 2, at least for rank universal sentences. And just as we would reject formalism, we have to reject that. But what about the continuum hypothesis then? Well, so I'll give you just a very brief sketch of how the continuum hypothesis might be resolved, and this is still by way of introduction, so I'll be talking much faster. If you have an infinite cardinal, H kappa is the union of all the transitive sets whose cardinality is less than kappa. This is another way to layer or decompose the universe of sets. So we had the V alphas, the rank hierarchy. This is another way to do it. And we could ask, how do these match up? Well, V omega, that's just H omega. V omega is really arithmetic. V omega plus 1, that's the reals. That's not equal to H omega 1, but it's equivalent. They're bi-interpretable. They're equivalent the way the integers and the positive integers are the same. What about V omega plus 2 and H omega 2? This is the next structure in this hierarchy. This is the next structure in the V alpha hierarchy. These are equivalent if and only if the continuum hypothesis holds. So maybe the correct next step in trying to understand V, the correct structure, we've understood this, that's projective determinacy. Maybe the next step is to try to understand this. And if you insist that this is the next step, I think that's an implicit bias for the continuum hypothesis. So let's concentrate on this. Well, determinacy was very successful for H omega 1. We have no idea what a generalization of determinacy to H omega 2 might be, but we could try to just abstractly look for generalizations. So we could say an axiom is a good axiom for H omega 2. It's got to be a rank existential axiom, and it can't be false. And then that one axiom in omega logic should decide all questions about H omega 2, and that's the formal thing. So if you take any sentence about H omega 2, interpreted in H omega 2, the axiom tells you whether the sentence is true or false. So one axiom gives you everything. Projective determinacy yields a good axiom for H omega 1. So what we're doing is taking that aspect of determinacy here, generalizing it to an abstract property, and just asking, are there any axioms? If there are a proper class of Woodin cardinals and the omega conjecture holds, then there is a good axiom. So there is an axiom satisfying this. In fact, there's a preferred axiom, but I'm not going to talk about that. Okay, but let's see what happens now. Suppose you had a good axiom, and it's actually true in V. So we're going to appeal to this theorem again, the fundamental theorem of omega logic, which says that the validities are definable in V omega plus 2. Well, then V omega plus 2 can't be equivalent to H omega 2, because otherwise the theory of H omega 2 would be definable in H omega 2, because omega logic is definable here. And that contradicts Tarski's theorem on the undefinability of truth. So we get a conclusion. Any good axiom has to imply that the continuum hypothesis is false. So if you're going to unravel H omega 2 by a generalization of determinacy, and that is in fact a good axiom, continuum hypothesis has to be false. So that's a prediction, if you want, that the continuum hypothesis is false. It's not a proof. It's not even an argument. It's just a prediction. Good axiom, it's just saying if you're going to have a simple, elegant theory for H omega 2, you must have the continuum hypothesis is false. Now you might infer from this, there is a problem here, is you can't go past H omega 2. You can't have a good axiom for V omega plus 2. So in this scenario, the last gasp of determinacy is unraveling this structure. You get an answer to the continuum hypothesis, and then you're done. You can't extend your understanding any further. All right, so the skeptic now is going to step in, because they're getting annoyed at this point, and they're going to say, look, the continuum hypothesis is neither true nor false, not because of Cohen's method of forcing, because the entire conception of the universe of sets is a complete fiction. So then they'll make a claim. All the theorems of set theory are finitistic truths. They're a reflection of us, not of any mathematical reality. And there are people who will hold this view. Okay, so here's the response. So that's the skeptic's challenge. How do you know that your entire development of set theory, as maybe even as beautiful as it is just not a reflection of our biology? And maybe if we could talk to dolphins, they'd have a different set theory. Theory of widgets, nothing to do with sets. Well, until we talk to dolphins or contact extraterrestrials, it's very hard to draw a line when you only have one point. All right, so here's my response. I'm going to make a prediction. And I guess there's going to be a record of this prediction. I predict that within the next 2,500 years, no formal contradiction in this theory, and I'm obviously biased to it, will be discovered by any means. This is a specific prediction about our world. It presupposes no meaning to the underlying mathematical concepts. It is not reducible to any mathematical theorem. So, in 2,500 years after this prediction has been verified, how does a skeptic account for this prediction? The skeptic has said, there's no sets, there's nothing. But this is a prediction born out of a belief that the universe of sets is meaningful. It's a prediction over 2,500 years. And this is a serious prediction. Okay? So I challenge you to come up with another prediction that you're willing to make over a similar time scale. 2,500 years is a long time. Go back 2,500 years. Compare mathematics then to mathematics now. All right, so now we want to investigate this prediction a little bit more. So I need to talk about a little bit about the hierarchy of large cardinal axioms. So this is our short version. Inaccessible cardinals, those were introduced in the early 1900s. Measurable cardinals, Banach in the 50s. Woodin cardinals, they came in around 85. Something called super strong. I'll give you a tip here. If you think of a large cardinal, don't give it any kind of reasonable name, because it will stick, right? And then someone else will write the paper and they'll have to name it after you. Solovay made that mistake. He introduced supercompact cardinals. That was a great name and it stuck. Extendable cardinals. Now there's a certain lack of imagination in the adjectives. Huge cardinal. Omega huge cardinal. Okay, so that's kind of the hierarchy. There's a corresponding hierarchy of predictions one could make, but I'm not prepared to make yet. Obviously, I'm making a prediction here. I wouldn't make this prediction quite yet, and certainly not here. So what I'm trying to say by making that comment is there's some kind of moving threshold where one makes the prediction. One wouldn't have made this prediction in the 60s. In fact, there were manuscripts circulated that purported to show there were no measurable cardinals. There still are. Okay, so it's by no means clear when these axioms are proposed that they're consistent. Now, for each of these large cardinal axioms, if the axiom holds in one universe of the generic multiverse, then it holds in all. Well, that's good. But there's a problem. None of these axioms is expressible by as either a rank universal or rank existential sentence. So that problem returns. If you're really going to use the generic multiverse as the basis for your conception of truth, and now you want to go beyond rank universal and rank existential sentences, you have to account for the restriction to set forcing, and it's fair to say there's no candidate. So at present, there's no candidate for a reasonable enlargement of the generic multiverse, which retains the feature that large cardinal axioms can be multiverse truths. And the point here is there seems to be no way to make the prediction of consistency other than to make the prediction of truth. So whatever your conception of truth is in set theory, unless you're going to say the large cardinal axioms are true, there doesn't seem to be a reasonable basis for saying that they're consistent. Why? All right, well, the skeptic is a clever person, and they're well read in set theory, so they're about to make a response. So before I do that, I have to tell you a little bit about the basic template for large cardinal axioms. This doesn't cover all large cardinal axioms, but it covers the hierarchy as we study it now. Basic template is there's a transitive class and an elementary embedding from V, that's the universe of sets, into that class. An elementary embedding is a function from the domain, V in this case, to the range, which preserves truth. Now you might object, wait a minute, you're talking about classes, where did they come from? Well, from almost everything I'm going to talk about, we can restrict to definable classes. So the use of class here is just like the use in number theory, talking about the set of all prime numbers. The set of all prime numbers is not a number, so a number theorist can't talk about that. It's not a number, but it's a definable collection of numbers. So it's a similar thing. Any such embedding, if it's not the identity, and we're not interested in the identity, there has to be an ordinal which is not sent to itself. The function has to be increasing on the ordinals. The least such ordinal is called the critical point. That's the large cardinal. So a measurable cardinal is just the first instance of this. Kappa is a measurable cardinal if there's an elementary embedding from V into M, and kappa is the critical point of J. How do you strengthen the axiom? You require M to be closer to V. Well, in the early 60s, that was realized, and so what do you do if you want to get the strongest axiom? You make M equal to V. And that was proposed by Reinhardt. He didn't call it a Reinhardt cardinal. In fact, they were never given a name, but I'm giving it, well, let's call it a Reinhardt cardinal. So kappa is a Reinhardt cardinal if there's an elementary embedding from V into V, where kappa is the critical point of J. Koonin showed, the published date is 71, but he did this in the middle 60s, there are no Reinhardt cardinals. So that's why they never got a name. Now, Koonin's proof makes essential use of the axiom of choice, and the problem is still open without that assumption. Now, even for much stronger versions of the axiom, the idea is, all right, maybe it's hard to refute Reinhardt cardinals in ZF, in other words, not using the axiom of choice, but if you really strengthen the axiom, it should be easier to refute, right? And maybe if you really strengthen it, you should be able to eliminate the axiom of choice. Maybe the Reinhardt cardinal is near some kind of threshold, and that's why it's hard. So an invented notion, we'll say kappa is a super-Reinhardt cardinal if there are many, many embeddings from V into V with critical point kappa. So here's a formal thing. And I should say both Reinhardt cardinal and this make essential uses of classes, but there are various ways to satisfy the assumption. So I'm not going to worry about it. Kappa is a super-Reinhardt cardinal if for each ordinal alpha you have an elementary embedding from V into V. Kappa is the critical point, but now the image of kappa is bigger than alpha. So you can move kappa up as high as you want by an elementary embedding. Here's the problem. Now the clever skeptic comes back. The formal consistency of that theory implies the formal consistency with ZFC of all large cardinal axioms not known to refute the axiom of choice, including all the axioms on the list I gave and quite a bit more. So now the skeptic says, I can make one prediction, that this theory is consistent, and that trumps all the predictions you self-proclaimed Platonists can make. So now the set theorist has a problem. How can they ever argue that this axiom is consistent? You can't do it because it's true. Because if this were true, you've given up the axiom of choice, and we don't want to do that. So any such argument would seem to require a completely different conception of large cardinal axioms. So the consistency claim was cited as an evidence for truth in set theory, or meaning to set theory. And I suggested this was a moving and evolving understanding. But here's this outlier, this one axiom, whose consistency implies the consistency of all the others. There's no mystery in explaining one prediction. There's a mystery in explaining a pattern of predictions. So the potential pattern of predictions of consistency in the large cardinal hierarchy gets reduced or trumped by a one instance prediction. Oops, oh there, that. So this is a problem. Okay, so now let's, a whirlwind view of inner models. So Gödel's constructible universe. So it's easy to describe once you understand the definable power set. So the definable power set, you have a set. The definable power set denotes not all the subsets of X which are logically defined in this structure from parameters. That's in contrast to the power set, which is the set of all subsets of X. So we had the cumulative hierarchy defined in terms of the power set operation. If you replace the power set operation by the definable power set operation, you get Gödel's constructible universe. So here it is. Again, you start with nothing. At a successor step, you just collect all the definable, you apply the definable power set, and at limit stages, you take unions. You look at the class of all sets you get. That's Gödel's constructible universe L. That is the universe that Gödel constructed. He showed that the continuum hypothesis is true in that universe. He incidentally also showed that the uniformization problem was true for the projective sets and that the measure problem was false. And I think he felt that was as important an application as the application to CH. Scott proved a remarkable theorem that got somehow overshadowed by Cohen's proof a few years later. You know, timing is everything in mathematics. If you have a measurable cardinal, V is not equal to L. This was the first indication that V might not be L. Now, I'll draw a corollary to this. Now, it's not a formal corollary, so I'll call it a meta-corollary. V is not L. Okay? Now, it's obviously not a formal corollary unless you assume a measurable cardinal. So this is the argument against V is equal to L. Well, we have a problem now, and that's the inner model problem. We would like to find generalizations of Gödel's construction of L that somehow yields enlargements in which large cardinal axioms can hold, because they can't hold in L by Scott's theorem, and somehow this should be related to occurrences of large cardinals in V. There should be an ancestry or a lineage. So how can we enlarge L? Well, there's a very easy way to enlarge L. Take any set E. We can relativize L to L of E. Here's the formal definition. The only change is at the successor step. We collect the definable subsets of what we have, just as we would in defining L, but now we add E intersect what we have. So we're just adding one more set at every successor step. It's E intersect what we have constructed at that stage. L of E is a class of all sets such that A is in L alpha V for some alpha. Notice if E intersect L is empty, then L of E is L. That's an easy transfinite induction. Okay, so that's how we're going to enlarge L. So now the problem is how to choose the set E. So the last technical definition I'm going to have to make. These are the building blocks for inner models. These are called extenders. So let's go back to our template. We have an elementary embedding from V into M. Has a critical point kappa. I'm going to impose an additional restriction for the moment. I have a ordinal gamma that's between the critical point and the image of the critical point. And I'm going to require that M contain a piece of V. V gamma is included in M. So here's the technical definition. The extender of length gamma defined from J is this relation. There it is. I'll tell you what it is. It's encoding, it's roughly encoding this function. If you have A, a subset of gamma, you take A to J of A intersect gamma. Now J of A is going to be a subset of J of gamma, and gamma is going to be less than or equal to J of gamma, so it's not even J on P of gamma. So it's some fragment of J. Okay, and it was introduced by Mitchell. Okay, so that's the formal definition. Okay, now you could take L of E for E an extender, and that solves the inner model problem for one measurable cardinal. Now again, I'm inverting history. Kunin's theorems predate the definition of an extender, but restating Kunin's theorem in the language of extenders, this is the theorem. Suppose you have two extenders. Well, they have associated critical points. And let's say kappa E is less than or equal to kappa F. Okay? If they have the same critical point, then remarkably the models are the same, even if the embeddings were different. When you take the fragment of the embedding and construct, they're the same. E may not equal F, but L of E will equal L of F. If kappa E is less than kappa F, then the L of F is actually a submodel of L of E, and there's an elementary embedding from L of E to L of F, which is definable in L of E. So that's part of the justification for the claim that this truly is an enlargement-like girdle that generalizes L. So it solves the inner model problem for a measurable cardinal, but not for two measurable cardinals. Same time, if E is an extender, L of E satisfies there's a measurable cardinal, but L of E satisfies there are not two measurable cardinals. So if you want to go beyond measurable cardinals for stronger large cardinals in a hierarchy, you can't construct from a single extender. You have to construct from a sequence of extenders. And that gets complicated because how do you choose the sequence? Maybe you're choosing the sequence. You have to be careful how you choose the sequence so that you don't code up unintended information. Okay? So that's the basic template for the inner models. And the basic problem is how to specify the sequence. That's the key problem. And it becomes quite complicated. So where are we now? The current state of the art are the inner models defined by Mitchell and Steele. It took about 20 years, starting in the early 80s to nearly 2000. There's unfortunately something which I'll call the Scott effect. The methodology is such that whenever you build one of these models, there's a corresponding version of Scott's theorem. In other words, you might target a certain axiom in the hierarchy, you go through all this work to build the enlargement of L for that axiom, and you don't get any larger large cardinals. Just as L doesn't have a measurable cardinal, if you build the inner model for 17 measurable cardinals, it doesn't have 18 measurable cardinals. If you build the inner model for one Woodin cardinal, it won't have two Woodin cardinals in it, and so forth. So the basic methodology seems to argue there can be no ultimate L. There's something wrong here. There's some fundamental misconception. All right, so now I have to go back to supercompact cardinals, which Solovay introduced in around 1966. Here's the formal definition. This is another axiom which is not captured by the existence of a single elementary embedding, many. So kappa is supercompact if for each ordinal alpha, you have an embedding from J from V into M. Kappa is the critical point. J of kappa is bigger than alpha. So far it looks like Super-Reinhardt, except M is not V. And now we require closeness of M to V. M has to have all functions from V alpha into M. So supercompacts were introduced, as I said, in '66. At that time, you had measurable cardinals, you had supercompact cardinals, and then you had huge and so forth. Here was not thought to be anything interesting. And that's where it turned out all the action was taking place as far as determinacy is concerned. Woodin cardinals and everything are all down here. Okay, so now I have to revisit the definition of an extender. Before, when I defined extender, I had this condition, and now we're going to relax that condition. Okay, and still extract the extender, same definition. If gamma is less than or equal to JF kappa, we'll call E to be a short extender, otherwise E is a long extender. The Mitchell-Steele intermodels, which are the current state of the art, are constructed from sequences of short extenders. But Steele identified a few years ago that the basic methodology encounters serious obstacles if you try to allow non-trivial patterns of long extenders, and long extenders are necessary if you want supercompact cardinals and beyond to exist in the intermodel. So the methodology identified a specific threshold. And remarkably, something really amazing happens. Here's the technical theorem. Suppose you are building your extender sequence and you've reached a supercompact cardinal, so this is now a class length sequence witnessed by the extenders on E. So here's the technical thing. Let me give you the short version of it. It's saying that if you build the extender model to reach a supercompact, it's suddenly closed under all kinds of extenders that aren't on the sequence. When you build intermodels with short extenders, the idea is you are creating all the extenders that are going to be in the model as on the sequence. Something miraculous happens at supercompact, and just reaching supercompact, you get a much stronger closure condition. And that explains the obstacle. If you tried to put those longer extenders on, they would interfere with the extenders being created by the sequence and code information that shouldn't be there. So we have now a paradigm shift in the intermodel program. We have the suggestion that there's an ultimate L. Any solution to the intermodel problem for one supercompact cardinal yields a maximal enlargement of L, which solves the intermodal problem for all stronger axioms of infinity. That's a theorem one can prove now. Okay? So that explains this threshold problem in the intermodal program. So where have we reached? The Mitchell-Steele models can go up to just shy of supercompact, but existence isn't quite that far yet. All right. What are the implications of ultimate L? So we don't know what ultimate L is, but we can infer a lot of the consequences. So I want to emphasize the existence of ultimate L is an open problem. So implication 1, assuming just ZF, there are no Super-Reinhardt cardinals. So that move by the skeptic to make the one prediction that trumps all the predictions we can make is eliminated. Okay? And it seems to reaffirm the idea that existence is the basis for consistency. This also would do something else. So Jensen is, I think probably is the prominent set theorist in the world. I think of Jensen as the successor of Gödel. He pioneered the intermodal program. He was the first one to develop the really deep analysis of Gödel's constructible universe. So I'll tell you 2 stories. Wait a minute. Is he going to see this? So I visited Berlin about 10 years ago. That was about just after the results about determinacy, and spent a sabbatical year there, and gave a colloquium talk at the Humboldt University. So I was talking about projective determinacy and making the grand declaration that projective determinacy is true. At which point, Jensen stood up addressed the audience and said, I just want you all to know that we don't all think projective determinacy is true. He had to rebut my claim. So he will not say that projective determinacy is true. So a few years later, I was walking with him after dinner, and I asked Ronald, it's Ronald Jensen, do you think projective determinacy is true? I mean, consistent. I know he thinks it's not true. And he said yes. So then I thought I had him. I said, well, wait a minute. How can you possibly think it's consistent if you don't think it's true? And his response was, axioms like that, determinacy axioms, large cardinal axioms, if they're inconsistent, they have a simple proof. There's no simple proof, we would have found it. Therefore, they're consistent. This is a counterexample. If this is how the inconsistency of this axiom goes, this is not a simple proof. This requires developing the whole theory of this ultimate L. This is going to be a book-length proof, or longer. This is going to be the result of a 20 or 30-year program of trying to understand the inner models. And in the end, you get the inconsistency. So you can't argue that the inability to find an inconsistency is evidence for consistency. Okay, there's another implication. Ultimate L, like the inner models, is constructed layer by layer. Large cardinals flow from V into ultimate L. So where they occur in ultimate L gives a stratification of the large cardinals. It explains, would explain the mystery of why do the large cardinals fall into a nice hierarchy, which has always been a cited mystery. Turns out that the omega conjecture has to hold an ultimate L. So no large cardinal hypothesis can refute the omega conjecture, because the large cardinal hypothesis itself would go down to ultimate L, and so it can't be refuted. I should have said, and I didn't, when I said the omega conjecture is open, it's not open whether the omega conjecture can hold. We know it's consistent that it holds. It's not known if it's consistent that it can fail. Okay? The final implication is a little bit more technical. It's new insights into the axiom of choice. From large cardinal axioms directly, you'll get definable versions of the axiom of choice. This is runs completely counter to the prevailing intuitions about the axiom of choice, which are intrinsically that the axiom of choice should be non-definable. And these axioms, these versions would be provable from large cardinal axioms. In fact, it's this that accounts for why you can eliminate the axiom of choice in proving there are no Super-Reinhardt cardinals. The Super-Reinhardt cardinal would give you the large cardinal axioms from which you could prove enough of the axiom of choice so that you could refute the existence of a Super-Reinhardt cardinal. Okay, so as I said in the abstract, I think we're at a real crossroads. So I'm going to pick 4 directions: north, south, east, and west. So the first crossroad is, does ultimate L exist? Well, it either exists or it doesn't. If it exists, we have a solution to the inner model problem for all large cardinal axioms. South, that would be the unfortunate direction. Ultimate L does not exist. Then we would have that the inner model program halts at the level of one supercompact cardinal, and we have to come up with a whole new way to try to understand large cardinals. And there's no hint at present what that approach might be. Okay, now I have to do east and west. Those are going to be predicated on the existence of ultimate L. Well, if ultimate L exists, we then have to ask, what is V? Remember, the argument against V is equal to L was that that denied large cardinal axioms that would seem not to apply to ultimate L. So not so easy to argue that V is not equal to ultimate L. So east is, one would have V is ultimate L, that we come to understand that V is ultimate L. Well, then we would have an unambiguous conception of V. We would settle the continuum hypothesis, the generalized continuum hypothesis. We would settle all the questions of set theory which have been shown to be independent over the last 40 years. We would have no mechanism for showing anything as independent of this axiom, any more so than we have in number theory. It would all be Gödel sentences, consistency statements. West is V is not ultimate L. So the current evidence, based on the analysis, is that V would have to be a specific generic extension of ultimate L, not a generic multiverse. But to validate this would require an absolutely astounding sequence of theorems about ultimate L. But we can't rule that out yet. I should point out that from the basic analysis that one can do now, one can already prove that ultimate L is itself a generic extension of a copy of ultimate L. So one might object that V can't be a generic extension. That doesn't seem right. But ultimate L is a generic extension. Not only is it a generic extension, it's a generic extension of an isomorphic, in some sense, copy of itself. It's isomorphic of a copy of itself into which it elementarily embeds. Okay, so I want to suggest that maybe we're about to enter a new age for set theory. One can already identify a sequence of questions such that depending on the pattern of answers, one will obtain a compelling argument for the continuum hypothesis, against the continuum hypothesis, or no evidence either way. And we can't rule out any pattern at present. If ultimate L exists, these questions will reduce, that's another feature of these questions, to questions about ultimate L itself. And so they will have answers. So this is a new aspect. Up to now, you can write down a series of questions. And if these answers are yes or no, you get penetrating new insights into the universe of sets. So what happens? Every time someone writes down these questions, we go off and we think about them, and we see these questions are unsolvable. In other words, you don't get yes and you don't get no. You get no answer. So you never make any progress. That's not going to happen now. You write down the questions. They're not going to be independent. You may need large cardinal axioms to solve them, but that's okay because the large cardinal axioms can hold an ultimate L. Then the issue becomes isn't whether you have undecidability. It's about the pattern of answers. Well, if we do this for 500 years and the pattern is always such that we never make progress, it's almost like there's an evil demon who's tempting us with problems, but the answers are always such that we never make progress. So if that were to happen, then I think you have to revisit the issue of the continuum hypothesis. Okay. All right, so I have to make my predictions as I close. My first prediction is ultimate L exists. Second prediction is I'm going for the miraculous route. V isn't ultimate L. Okay, I'm less confident of that prediction. If that holds, I'm going to predict that the continuum hypothesis is false. Okay, the GCH will hold asymptotically. And my last prediction, this is not going to take 2,500 years. So I really think that we're at a critical crossroads in the subject, and the next few years are probably going to give real insight into what direction we're headed. And I think there's a real chance that when we come through this period, we will have a conception of V that's as unambiguous as the conception of the integers. And that this whole period of independence was just that. It was an age of emerging understanding. It just took a while to get the axioms. You know, unlike the other areas of mathematics and set theory, we're still trying to find the axioms. And now, for the first time, there's evidence that we can have an axiom, formal axioms, which crystallize out the universe of sets, compatible with all large cardinal axioms, and are unambiguous, give us an unambiguous conception of the universe of sets. And I think if that happens, and however long it takes, it will really be remarkable. And it will then come back to these evolving consistency claims. There'll be a new way to advance our consistency claims. And I think there'll be a series of these claims. There'll probably be axioms that come up and it's not clear whether they're consistent or not. We'll understand them and then advance that frontier of consistency. And if there is a pattern of that through the years, of axioms, large cardinal axioms discovered and later validated, consistency claims made that aren't overturned, the longer that goes, the harder it is for the finitist to account for that. Unless the finitist can explain the large cardinal hierarchy, looking only at finitistic notions. And So what would be remarkable is if from finitistic notion, from miniaturization or finitistic considerations, one would have predicted that Reinhardt cardinals are inconsistent. But that didn't happen and hasn't happened. The prediction that Reinhardt cardinals are inconsistent comes from the point of view that the universe of sets is meaningful. We can't have a failure of the axiom of choice. We can't have the truth of the Reinhardt cardinal. The Reinhardt cardinal is stronger than all the large cardinals, therefore it's probably inconsistent. Okay? And there's been never another argument put forth. And I should say, and I will end, I promise, with this, Reinhardt cardinals have been used. The first consistency proof for projective determinacy was from Reinhardt cardinals. And I did that in the late 70s, 5 years before the Martin-Steele theorem. So the Reinhardt cardinals were fruitful. You know, people will cite large cardinals or a test for large cardinals. If the large cardinal hypothesis enables you to prove a theorem, even if that theorem is later proved by other hypotheses, if that first proof was from large cardinal axiom, that seems to be some kind of vindication for that axiom. And Reinhardt cardinals, again, be a counterexample to that. So thank you for your attention. Thank you for coming.